class. Today we're going to study what we chemists like to refer to as the mole. And the mole is really the bread and butter of chemistry. This is what chemistry is really made of. It deals a lot with this number right here, 6.02 times 10 to the 23rd power. And if you think about that number and how big it is, 6.02 times 10 to the 23rd, you move the decimal over 23 places, and you get this giant number right here. Now, you and I have a concept of what a million is. We have an idea of what a billion is. Even trillions has been thrown around lately. This is where our national deficit is, in the trillions. But let's make that a little bit bigger. If we had 100 trillion, we could get a quadrillion. 100 quadrillion would be a quintillion. And 100 quintillion would be a sextillion. We're talking about 602 sextillion. That is a huge number. And when we talk about chemistry, this is the magnitude of how many molecules are reacting in certain reactions. So we're going to deal a lot with what this is. 602 sextillion, huge number. We'll explore how big this is later. So let's define the mole. The mole is really just a method to group a large number, very similar to what you would do with a dozen. So let's say we had 12 eggs. If we had 12 eggs, we would say we had 1 dozen eggs. We just group them together, right? 12 eggs equals a dozen eggs. So if your parents send you to the store, they're not going to say, hey, go buy 24 eggs. They're going to say, go buy 2 dozen eggs. It's easier to group them than it is to count individual eggs for some reason. The mole is very, very similar to that. If we had a mole of eggs, we would have 6.02 times 10 to the 23rd, or 602 sextillion eggs. That's a lot of eggs. And you might think, why would I need that many eggs? Who are you making cookies for? I don't really know. But we don't really use the mole to talk about eggs and things that are larger in nature, but we use it to talk about atoms and molecules, because a mole of molecules doesn't actually take up a lot of space. 602 sextillion molecules is very easy to come by, because molecules are very, very, very small. So rather than talking about scientific notation and how many molecules we have, we'll say we have a mole of molecules. It's easier than using scientific notation, and we group them together. You can kind of see here on this scale, this picture, if you have a mole of something, 6.02 times 10 to the 23rd, you have 1 mole of it, and there's a picture of a mole. This number, 6.02 times 10 to the 23rd, is named after a very famous scientist whose name is Avogadro. It is known as Avogadro's number. You need to know that. Avogadro's number, 6.02 times 10 to the 23rd. And if you can see here, the way we have this arranged, it looks like a conversion factor, very similar to what we use in dimensional analysis. So let's talk about how we're going to use this in chemistry. Well, if we have a mole of something, we have 6.02 times 10 to the 23rd of that substance. We say, in general, we talk about particles, okay? This can be atoms or molecules. So let me get some conversion factors. Let's say I had 1 mole of iron atoms. Iron is by itself, it's an atom. 1 mole of iron atoms means I have 6.02 times 10 to the 23rd atoms of iron. Okay? It's very important that I write iron on both sides of this conversion factor, because I need to include iron on both sides. If I'm talking about molecules, let's say I had water. If I had a mole of water, H2O, water's a molecule, 2 things combined, bonded. If I had a mole of water, I would have 6.02 times 10 to the 23rd molecules of water. 6.02 times 10 to the 23rd molecules of water. So this is our general format for our conversion factors. If you have a mole of something, anything, X, you have 6.02 times 10 to the 23rd of that substance. It's just a number to group it. So what does that mean in chemistry? Well, it's very similar to what we just showed on the last page. We can use this as in dimensional analysis with conversions. So let's say for a minute I had 5.83 moles of iron and I wanted to know how many atoms that was. Well, here's my conversion up here, and if I put iron in, I can use that as a conversion. Start out at 5.83 moles of iron, so 5.83 moles of iron over 1. And if I set up my T-chart, moles of iron is on the top, so I need moles of iron on the bottom. So 1 mole of iron is going to come down here. And on the top then, the other part of my conversion is 6.02 times 10 to the 23rd atoms of iron, because iron is an atom. Moles cancel out, and using dimensional analysis, I can multiply 5.83 times 6.02 times 10 to the 23rd. I start with 3 significant figures on the left in my problem, 3 sig figs. So I need 3 to end with, and my answer is 3.51 times 10 to the 24th atoms of iron. Okay? If I wanted to do it the other way, I could do it the other way too. If I start with atoms, I could very easily go to moles using the same conversion factor. I'm starting at a different point now, so let's look at this. 4.82 times 10 to the 24th atoms of iron. That's going to go over 1. I need to make my T-chart. And now my Avogadro's number is going to have to go on the bottom, and 1 mole of iron is going to have to go on top. So 1 mole of iron is going to be equal to 6.02 times 10 to the 23rd atoms of iron. Atoms cancel out, and my units are in moles, so if I divide Avogadro's number, or if I divide 4.82 times 10 to the 24th by Avogadro's number, I have 3 sig figs over here to start with. So I need to end with 3. My answer is going to be, how many moles do I have? I have 8.01 moles of iron. So I can use that as a conversion factor. Okay, let's look at a different problem now. I can use the same thing talking about molecules. So if I have 2.19 moles of water, water is a molecule, I can convert to molecules using the same exact conversion. 1 mole of water equals 6.02 times 10 to the 23rd molecules of water. So let's set it up. 2.19 moles of water. Use my T-chart. Plug in the conversion. Moles on top here, so I need 1 mole on the bottom. 1 mole of water is 6.02 times 10 to the 23rd molecules of water. Three significant figures, and I get 1.32 times 10 to the 24th molecules of water. Okay? We're just using 1 mole equals Avogadro's number as a conversion factor to solve some of these problems. The last one, I can go the other way with molecules as well. If I have 7.21 times 10 to the 21st molecules of water, set up my T-chart over 1, and I know that for every 6.02 times 10 to the 23rd molecules of water, I'm going to get 1 mole of water. So look at all these problems and look at what they have in common. I'm using the same conversion different ways, talking about atoms and molecules to convert between particles and moles. 3 significant figures here to start with, 7.21. So I need to end with 3 significant figures, and with rounding I get 0.0120 moles of water. Molecules of water are going to cancel out, so I'm left with moles. Just using it as a conversion factor. And that's really all we're going to do with the mole, so you need to be able to define it and use it as a conversion factor between between particles and moles.